Alright, howdy. Um, Today we'll begin a presentation over mapping GPS denied areas. And the team members are Brendan Lever, Paul Intakeo, Bryan Agosto, William Kennedy, Colin Goralczyk, and Mike Danen. So to start off with the background, GPS technology has only recently emerged and being incorporated into everyday life. This technology has allowed us to do things that were unimaginable only a few short decades ago. Things like navigation and mapping have greatly improved with the addition of GPS technology. However, GPS is not perfect. It requires line of sight, and this means that despite GPS wide array of satellites and coverage, there are some areas that are not accessible with GPS. We refer to these areas as GPS denied areas. The study aims to act as a proof of concept for mapping GPS denied areas. We propose that the GPS denied areas can be mapped accurately by using a LiDAR to create a point cloud, which can then be tied into a coordinate system by georeferencing it with known points.
So why is this important? Mapping GPS-denied areas can prove to be beneficial for many different reasons. Perhaps the most important way it can prove beneficial is that it could be done quickly and remotely. It could aid first responders or military personnel, increasing situational awareness for potentially dangerous operations. Mapping buildings can also be useful for simple visualization purposes. Creating a 3D model for a building can be used for potentially limitless applications, ranging from tourism to real estate to construction.
Next, we'll talk about the research question and our hypothesis. In this study, our goal is to answer this question: can GPS-denied areas be mapped accurately? And we hypothesized that yes, GPS-denied areas can be mapped accurately because LiDAR scans can be taken in a GPS-denied area. These scans can then be tied into a coordinate system by georeferencing it to known points collected with an RTK GPS. Now we'll talk about our methods section. The study site we chose was the O&M building on campus. We started on the outside and then traversed into the first floor of the building. We chose this building for a few different reasons. Firstly, the building has a lot of details both on the outside and inside. These details are important because when georeferencing data, it helps to have prominent features that can be distinguished in point clouds.
Our experiment, we used a variety of equipment. For our LiDAR scan, we used a Faro X30 laser scanner and a tripod. For our survey, we used a Leica RTK GPS and Leica TS15 total station and survey pole. We used a 360 prism to mark our backsite and foresight. We also used a measuring tape to measure our instrument height.
For our data collection, we started off by collecting our LiDAR point cloud. We did this with help from Dr. Glowacki and a graduate student, Benjamin Bask, from the Department of Architecture at Texas A&M University. We conducted 3 scans outside, starting on the quad outside of O&M, and slowly worked our way towards the front door to the building. We then conducted 1 scan inside. With our LiDAR data collected, the next step was to conduct a survey that could be used to georeference the LiDAR data. We used an RTK GPS to establish 2 known points. Before we were able to use the known points for the total station setup, we had to convert the northings and the eastings into latitude and longitude by converting US feet to meters. Once we set up the total station over 1 known point and shot the other known point as the backside, we used reflectorless scanning to shoot 10 points outside of the building on distinct features that could be easily identified in the point cloud. We then traversed into the building using a 360 prism to identify a point inside of the building. The total station was then moved onto this point, with our initial point being used as a backside. We then used reflectorless scanning to shoot 13 more points inside of the building again, using distinct features that would be easily identified in the point cloud.
As you can see, these pictures show all the points that were recorded using reflectorless scanning. The red dots indicate a distinct feature where a point was recorded. These points would be used to then georeference the LiDAR data that we collected.
So for our data processing, we switched around between a few different programs before we eventually settled on Trimble Business Center, right? I know we tried Global Mapper, and we tried Autodesk, right?
We tried Autodesk Civil 3D.
Yeah, that's right. IntelliCAD, right? Is that
Yeah.
But,
And the issues we faced with that were licensing issues.
yeah, lots of licensing issues.
Yeah.
But so we eventually got it done in the Trimble software, in Trimble Business Center, and first thing we did is we pulled in the data, and then we set the projection. And so for this project, our survey data was in NAD 83 State Plane, Texas Central. So that's what we set it to, and then we created two different 3D views. It's important to note these two different views are on the same workspace. And so just on the left, you can see here that we have our LiDAR data. On the right is our survey data, which is tied to a coordinate system. But before we get started on the data processing, it's just important to note that the preliminary processing of the LiDAR data was conducted by Ben Bask and Dr. Glowacki in the Department of Architecture. They were nice enough to let us borrow their Faro X30 3D scanner, so that was really awesome.
So here in the video, you can see we started to georeference the LiDAR data to the survey data. This process is exactly the same as georeferencing to 2D data. You just click the point on the LiDAR data and then match it up to the points on the survey data.
Yeah, and you can do this as many times as you want, pretty much as long as there's a minimum of 4 points. After a while, you start to see sort of diminishing returns, so you don't want too many points, but you want to make sure you have at least 4.
Yeah, so once you georeference all the points, you just click apply, and then you should see the LiDAR data shift to where the survey data is.
Right here, we're just going to click yes, and we're going to create a what's it called?
It's just the transformation results page.
Right, a transform surveys report, or survey points report. And so what this is going to tell us is it's going to tell us our residuals and how everything came out. So we'll get more into that later, and we'll show that a little bit later on. But right here, you can see there's our LiDAR data was pulled over and matched up with our survey data, and you can see the big white points right there, and you can see right there's our front sight, and our back sight is right there also. So matched up pretty well. We had pretty low residuals, so that was good. And yeah, so here you can see the inside of the building. Again, a lot of the survey points are matched up. You can see 4 points right there on the elevator door, and then 2 points there against the back wall, up in the bottom corner and in the lower corner. And yeah, so there's our front sight.
That's where our initial total station setup was, and that's also where the Faro LiDAR scanner was set up as well. That's why there's a big black circle over there.
Here we're removing the LiDAR data and then showing it again, and you can see just to demonstrate how our survey points are there lined up along with our LiDAR data. So there you can just see that again. There's all our survey data. Then we're going to add the LiDAR layer back, and you can see it's all matched up really nicely. And so this is our transform survey points report. So we created this after we finished our georeference, or after we finished georeferencing our LiDAR data. And the big thing I want to point out here is that you can see our overall residual up there in the top left, and the standard deviation was 0.069 meters. So we had very low residuals, and that indicates that our data was georeferenced pretty accurately. So that's really good to see.
With this in mind, it's also important to note that the equipment that we were using was LiDAR as well as RTK. It's state-of-the-art equipment that we were using. And with that being said, that's why inconclusive our standard deviation and our researches were so low, less than a tenth of a meter of accuracy. So that's very important to note. So to conclude, initially our study site was going to be Inner Space Caverns in Georgetown, Texas, and we were only going to conduct a survey and traverse into the cave to map a route. But this didn't really pan out due to the issues with the equipment and the time constraints. So we ended up switching our study site to the O&M building on campus. While this is a less interesting study site, it's still a GPS-denied area, and functionally, the site proved to be a very good choice due to being on campus.
However, if we were to have conducted the study at the caverns, the margin of error would have been far greater due to the team producing more total station setups. In this case, at O&M, we only had 2 total station setups. Since the study was now being conducted on campus, a LiDAR scanner was able to be secured for the project. This allowed our results to be significantly more accurate, with the caveat that the LiDAR data would simply have to be georeferenced to a survey. However, the LiDAR data did initially give us some trouble. The trouble mostly stemmed from our inexperience with working with point cloud data, but issues faced were resolved with the help from outside sources. Issues were also faced with unit conversion to convert feet to meters using Google's built-in unit converter. However, this converter uses international feet rather than US feet. This inconsistency was apparent when we brought the data into ArcGIS Pro, and then it was converted into the proper units.
Ultimately, the project was a success, and we were able to effectively map the inside of the building by georeferencing LiDAR data. This proves our hypothesis that GPS-denied areas can be mapped accurately by georeferencing LiDAR data using survey data tied to a coordinate system. Not only does this method provide accurate results, but it allows results to be highly detailed. Since this method is heavily reliant on survey data, human error is where most of the discrepancy will likely originate. This error will be magnified depending on the number of total station setups being used to traverse into the GPS-denied area. The greater the distance that needs to be traversed, the higher the likelihood of human error. Error can also be introduced from processing the data. Georeferencing must be done carefully, or there is a risk of introducing more error.
So this study is sort of acts as a bit of a proof of concept, and so for future research, there's a lot of areas that a lot of directions that this can go, and some of them just include mapping indoor areas autonomously or remotely, and also developing a method or modifying our method that would be able to perform faster than a standard survey, because as it stands right now, this method is fairly time consuming. We have to do a whole bunch of LiDAR scans and then also a survey. So